When grounding remote single-phase motors, particularly in coastal environments, several key considerations can improve safety and reliability. A crucial aspect is establishing a robust and continuous ground path. One effective method is to implement a ground ring conductor. Install a number 8 or larger American wire gauge copper wire around the circumference of the main 2-inch polyvinyl chloride conduit loop. At each hand hole, connect the ground ring to the equipment ground conductor inside. This provides a continuous ground path, even when the hand holes are submerged in water. This approach ensures that a low impedance ground fault path is maintained, enhancing the effectiveness of overcurrent protection devices. For ground wire connections, consider using a junction box in each hand hole. Join all the number 10 ground wires for the motors in the junction box, utilizing mechanical ground lugs or wire nuts. Subsequently, connect the joint ground wire to the equipment ground conductor. This method provides a central point for grounding connections, facilitating inspection and maintenance. An alternative approach involves using a grounding tap on the inside of each 1-inch conduit. Splice the number 10 ground wire for the motor to the grounding tap. This eliminates the need for splices in the ground wire between the hand hole and the motor, reducing potential points of failure and simplifying installation. In addition to these grounding techniques, best practices include applying anti-seize paste to all ground connections to prevent corrosion. This is particularly important in coastal environments where exposure to saltwater can accelerate corrosion. The anti-seize paste creates a protective barrier, maintaining the integrity of the ground connection over time. If any splices are unavoidable in the well vault, ensure they are waterproof. Use heat shrink tubing or other moisture-resistant materials to protect the splice from water intrusion. Waterproof splices are essential for preventing corrosion and maintaining a reliable ground connection. Finally, it is crucial to test the grounding system to verify its continuity and integrity. Use a ground fault circuit interrupter to test the grounding system. This ensures that the grounding system is functioning correctly and can effectively protect against ground faults. Implementing a ground ring conductor offers several advantages. Firstly, it provides a continuous ground path even when the hand holes are flooded. This is critical in coastal environments where water intrusion is common. Secondly, using grounding taps minimizes splices in the ground wire between the hand hole and the motor. Reducing the number of splices decreases the potential for failures and simplifies maintenance. A well-grounded system is paramount for the safety of personnel working with electrical equipment. A properly grounded system ensures that fault currents are safely conducted back to the source, minimizing the risk of electric shock. Selecting the appropriate size of the equipment grounding conductor is critical for electrical safety and code compliance. The National Electrical Code, or NEC, provides guidelines for determining the minimum size of equipment grounding conductors based on the rating or setting of the overcurrent protective device in the circuit. For a circuit breaker rated at 20 amps, an EC table 250.122 typically requires a minimum of number 12 American wire gauge copper conductor for the equipment ground. However, since number 10 American wire gauge is already being used for the phase conductors to mitigate voltage drop, maintaining the same size for the equipment grounding conductor can provide additional safety margin and improve the overall performance of the grounding system. The use of number 10 American wire gauge for the equipment grounding conductor ensures that it has sufficient ampacity to safely carry fault currents back to the source in the event of a ground fault. This helps to quickly trip the circuit breaker, minimizing the duration of the fault and reducing the risk of electrical shock or equipment damage. Moreover, using a larger equipment grounding conductor can also help to reduce voltage drop in the grounding system, which can be particularly important in long circuit runs or in systems with sensitive electronic equipment. Lower voltage drop in the grounding system improves the effectiveness of the grounding system in protecting against electrical noise and interference. When installing the equipment grounding conductor, it is essential to ensure that it is properly connected to all metal parts of the electrical equipment and to the grounding electrode system. This includes connecting the equipment grounding conductor to the motor frames, the metal enclosures of the motor starters, and the metal conduit or cable trays that support the electrical wiring. Proper bonding of all metal parts ensures that they are at the same electrical potential, minimizing the risk of electrical shock in the event of a ground fault. In addition to the size and installation of the equipment grounding conductor, it is also important to consider the type of grounding electrode system used to ground the electrical system. The NEC specifies several types of grounding electrodes that are permitted, including metal underground water pipes, concrete encased electrodes, ground rings, and ground rods. The choice of grounding electrode system depends on the specific site conditions and the requirements of the local electrical code. In coastal environments, where soil conditions may be corrosive, it is important to select a grounding electrode system that is resistant to corrosion and that will provide a reliable ground connection over the life of the electrical system. Concrete encased electrodes and ground rings are often preferred in these types of environments because they provide a large surface area for contact with the earth and are less susceptible to corrosion than ground rods. Proper selection and installation of the grounding electrode system are essential for ensuring the effectiveness of the grounding system and protecting against electrical shock and equipment damage. Ground fault circuit interrupters, or GFCIs, are an important safety device that can help to protect against electrical shock in wet or damp locations. GFCIs work by monitoring the current flowing in the circuit and quickly tripping the circuit breaker if they detect a difference in current between the hot and neutral conductors. This difference in current indicates that some of the current is leaking to ground, which could be a sign of a ground fault. GFCIs are typically required by the NEC in locations where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor areas. In the case of the remote single-phase motors in the coastal environment, it would be a good practice to install GFCIs on the motor circuits to provide additional protection against electrical shock. GFCIs can be installed in the motor control panel or at the individual motor disconnect switches. It is important to select GFCIs that are rated for the voltage and current of the motor circuits and that are suitable for use in the wet or damp environment. Regular testing of the GFCIs is also important to ensure that they are functioning properly. The NEC requires that GFCIs be tested monthly to verify that they are tripping properly when a ground fault is detected. Testing can be done using a GFCI tester, which simulates a ground fault and verifies that the GFCI trips within the specified time. Proper installation and maintenance of GFCIs can significantly reduce the risk of electrical shock in wet or damp locations. Surge protection is another important consideration for electrical systems, particularly in areas that are prone to lightning strikes or power surges. Surge protective devices, or SPDs, work by diverting excess voltage from the electrical system to ground, protecting sensitive electronic equipment from damage. SPD are typically installed at the main electrical panel and at individual equipment locations. In the case of the remote single-phase motors, it would be a good practice to install SPD at the motor control panel to protect the motor starters and other electronic equipment from damage due to power surges. SPD can also be installed at the individual motor disconnect switches to provide additional protection. It is important to select SPD that are rated for the voltage and current of the electrical system and that are suitable for use in the coastal environment. Regular inspection and maintenance of the SPD is also important to ensure that they are functioning properly. The NEC provides guidelines for the selection and installation of SPD. Proper installation and maintenance of SPD can significantly reduce the risk of equipment damage due to power surges. In addition to the technical aspects of grounding and protection, it is also important to consider the administrative aspects of electrical safety. This includes developing and implementing a comprehensive electrical safety program that includes training for employees, regular inspections of electrical equipment, and procedures for responding to electrical emergencies. Employees who work with electrical equipment should be trained on the hazards of electricity and on the proper procedures for working safely around electrical equipment. Training should include topics such as lockout/tagout procedures, the use of personal protective equipment, and the proper procedures for responding to electrical emergencies. Regular inspections of electrical equipment should be conducted to identify any potential hazards, such as damaged wiring, loose connections, or overloaded circuits. Inspections should be conducted by qualified personnel and should be documented. Procedures for responding to electrical emergencies should be developed and implemented. These procedures should include steps for shutting off power to the affected area, providing first aid to injured personnel, and contacting emergency services. By implementing a comprehensive electrical safety program, organizations can significantly reduce the risk of electrical accidents and injuries. In the context of the remote single-phase motors, several additional considerations are worth noting. Firstly, ensure that all electrical work is performed by qualified and licensed electricians who are familiar with the NEC and local electrical codes. Secondly, use only approved electrical equipment and materials that are suitable for use in the coastal environment. Thirdly, implement a regular maintenance program for the electrical system, including periodic inspections, testing, and repairs. Fourthly, keep accurate records of all electrical work, including as-built drawings, inspection reports, and maintenance records. Fifthly, provide adequate lighting in the handholds and well vaults to ensure safe working conditions. Sixthly, ensure that the handholds and well vaults are properly ventilated to prevent the buildup of hazardous gases. Seventhly, implement a lockout/tagout procedure to ensure that power is de-energized before any electrical work is performed. Eighthly, use appropriate personal protective equipment, such as rubber gloves and safety glasses, when working with electrical equipment. Ninthly, be aware of the potential for wildlife to enter the handholds and well vaults, and take steps to prevent this from happening. Tenthly, develop a contingency plan for dealing with power outages or other electrical emergencies. Furthermore, consider using corrosion-resistant materials for all electrical components, such as stainless steel or fiberglass, to extend the life of the equipment and reduce maintenance costs. Also, regularly inspect the grounding system for corrosion and make repairs as needed. Additionally, implement a program for managing vegetation around the electrical equipment to prevent it from interfering with the equipment or creating a fire hazard. Consider using remote monitoring systems to monitor the performance of the motors and electrical system, and to detect any potential problems early on. Explore the use of energy-efficient motors and controls to reduce energy consumption and operating costs. Keep abreast of changes in the NEC and local electrical codes, and update the electrical system as needed to comply with the latest requirements. Finally, foster a culture of safety among all employees and encourage them to report any potential hazards or concerns. By following these best practices, it is possible to ensure the safe and reliable operation of the remote single-phase motors in the coastal environment. Proper grounding, protection, and maintenance are essential for preventing electrical accidents and injuries, and for extending the life of the electrical equipment. Regular inspections, testing, and repairs are also important for identifying and correcting any potential problems before they can lead to more serious consequences. Furthermore, it is important to stay informed about the latest electrical codes and standards, and to update the electrical system as needed to comply with these requirements. A comprehensive electrical safety program that includes training, inspections, and procedures is essential for creating a safe working environment for all employees. By prioritizing electrical safety, organizations can protect their employees, their equipment, and their reputation.